Welcome to this lecture series in group theory. In this lecture, we will be revisiting the first isomorphism theorem and we will be looking at a sort of a generalization of it. And then we'll look at some applications of the first isomorphism theorem. So let us recall a few things. So suppose we have any function from a set x to a set y, then we saw that we can obtain a new function, which we denote by f bar in the following manner. So tilde denotes the fiber relation. I probably did not use this phrase, and I don't even know if this is a standard phrase. But by tilde, I just mean the equivalence relation on x defined in the following way: x tilde y if and only if fx equals fy. One can easily check that this is indeed an equivalence relation. And this notation denotes the set of all the equivalence classes under the relation tilde. Okay, and this map, the vertical, this guy is x going to the equivalence class of x, and I will put a tilde in the subscript to emphasize that the equivalence classes are taken under the equivalence relation tilde. So this is that map, and f bar is the map which takes equivalence class of x to f of x, and this is well defined simply by the definition of tilde. And clearly this diagram commutes, meaning what? Meaning you start with a element of capital X, you hit it by f, or you go via this route, it's the same thing. There is no difference in the obtained value in y. Okay, so this commutes, and diagrammatically what is happening is we have this set x and we have the set y, and if we denote these, the fibers of f by these, boxes sort of, and we collapse every box into a single dot, 1 2 3 4 5 6 in my picture. So then these dots denote the equivalence classes. This dot corresponds to that, the second dot corresponds to that, and so on. And then we get a map like this. F bar, this is f, and this is the function. Typically we denote this by pi. Okay, and note that this function f bar is injective. This probably I did not emphasize before, but this is an injective function. That is easy to check. All right, because whatever f was identifying, we have already identified, and therefore you can easily prove it formally. So we just exported this to the setting of groups. Instead of an arbitrary map, we have a group homomorphism between two groups, and we saw that the set of all the fibers is precisely G mod kernel phi. Here the set of all the fibers was denoted like this. Here the set of all the fibers is clearly G mod kernel phi. One can check that. And we saw that we can endow this with a natural group structure in the sense that this becomes a group homomorphism and that becomes a group homomorphism. In fact, only insisting that this becomes a group homomorphism already narrows down the group structure to a unique one. So there is a unique group structure here such that this becomes a group homomorphism, and then this automatically becomes a group homomorphism. And in the process, what we have done is that we have obtained a smaller group and a group homomorphism from the smaller group to this target group H, and this is injective, again for set theoretic reasons. So this is an injective group homomorphism. Right, and this is what we call the first isomorphism theorem. In this lecture, we'll saw a little bit of a generalization of it. All right, and then all this business motivated the notion of normal subgroups as to what subgroups n of a group G have the property that the set of all the left cosets G mod n admits a group structure such that this natural projection map G going to Gn is a group homomorphism, and we saw a bunch of properties of normal subgroups. All right, so these are the problems, and now let us get started with the material of this lecture. So again, start with a set theoretic setting. We have a function from a set x to a set y, and suppose we have an equivalence relation on the set x which is finer than the fiber relation tilde. The fiber relation we just discussed. Again, let me recall. We have x1, or rather x tilde x prime if and only if fx equals f prime. Did I use y in this thing? Okay, very bad notation. I should have used x prime. Yeah, so that's the relation tilde. It's an equivalence relation, which I'm calling the fiber relation. But what is meant by finer? So we say that this is finer than tilde if every equivalence class under this symbol is contained in some equivalence class under the fiber relation. So this is what we mean by finer, and let us see diagrammatically what it means. So we have a set x and the function f going to y. Let's say these boxes denote all the fibers. Then basically the equivalence classes of tilde look kind of like this. They partition the equivalence classes of tilde. Sorry, what did I say? The equivalence classes of, not tilde, equivalence classes of this guy, whatever this symbol is called, partition the equivalence classes of tilde. So this is one equivalence class of this symbol, this is another equivalence class, and so on. So every equivalence class of this guy is contained in some equivalence class of tilde, meaning contained in some fiber of f. The equivalence class of tilde are precisely the fibers of f. Okay, so then what we want to say is that one can factor out f in this fashion. This is also something we denote by f bar. It's kind of an abusive notation. What is this map pi? Pi is again x going to the equivalence class under this symbol, and f bar just takes an equivalence class to f of x. Now again, f bar is defined by representatives, so we need to check well-definedness, but that is clear because if this is equal to x prime, if this equation holds, then that means x and x prime are in the same equivalence class under this equivalence relation denoted by that. And therefore, they are also in the same equivalence class under tilde, because any equivalence class under this guy is contained in some equivalence class under tilde. And therefore, x and x prime are in the same fiber, and therefore fx equals f of x prime. So if you have two different representatives of the same equivalence class, they will have the same image under f bar. So this is well defined. So this is sort of a generalization of what we saw earlier. Previously, we were factoring out by x mod tilde. Now we are being a little bit more careful that we have a finer equivalence relation, and we are saying that maybe we don't want to identify all of the things in one shot. We'll identify some of the things. And yeah, so that is just one simple set theoretic consequence. Okay, it's just that this may not be injective. This will be injective precisely when this guy coincides with tilde. So that's the only thing. Here, f bar may be further identifying things in here, meaning f bar is not necessarily injective. So this is sort of a generalization of the set theoretic quotienting that we discussed, and now we can use this in the group theoretic setting. So now suppose we have a group homomorphism from a group G to a group H, and suppose we have a normal subgroup of the group G such that this normal subgroup is contained in the kernel. Then each left coset of n is contained in some left coset of the kernel. In fact, this implies that Gn is contained in G kernel phi for all G. So every left coset of n is contained in some left coset of the kernel. And by the same kind of reasoning we saw in the set theoretic setting, we have this factoring. Except that phi bar now need not be injective. It will be injective precisely when n equals the kernel. Right, and this is pi. Pi is just G going to Gn. And phi bar is Gn going to phi G. So this is basically, this diagram commutes for set theoretic reasons, and phi bar is still a group homomorphism. So all I'm trying to say is that you may not necessarily factor out entirely by the kernel in one shot. If you can find a normal subgroup that is contained in the kernel, you may factor out by that. Now, when one should not factor out completely and whatnot, that depends on the situation. Of course, you would take n as the trivial subgroup. Then this factoring is not giving anything. Then phi bar is essentially just phi. So this could be completely useless if you do not have a good normal subgroup with you, which is pertinent to the situation that you are considering. But nevertheless, this is a fact that you can factor out by G mod n or via G mod n through the natural projection and obtain a group homomorphism with domain with domain a potentially smaller group. All right, so this is it. This is the generalization that I wanted to discuss. And now let me get into applications of the first isomorphism theorem. Just very simple applications. And how to use the first isomorphism theorem. So suppose n is some positive integer at least 2, and that is not exactly necessary, but I have kept it like that for expository convenience. And let G be the group of all the nth roots of unity. So this G is a subset of the unit circle, and this is a group under the usual multiplication of complex numbers. So then this group and that group are isomorphic. Note that Z mod nz is precisely the quotient of Z by the normal subgroup nz. Z is an abelian group, hence nz, a subgroup of it, is a normal subgroup, and hence it is legitimate to consider the quotient. When we first defined Z mod nz, we just directly gave the definition that this is all this is the set of all the remainder classes modulo n, and we defined the group structure as to how to add remainder classes and whatnot. But now with the machinery of quotienting in hand, we can just say that, well, there is a group and there is a subgroup, which is of course normal because there is a Boolean. So we can consider the quotient group. And one can easily check that the description that we gave by fiat is same as the description that you get when you think of it as a quotient group. So I should have mentioned this earlier when we were discussing quotients, but anyway, I'm doing it now. So we'll just think of it as quotient of Z modulo nz, and we will show that this is isomorphic to G. And now the first approach that might come to mind is to throw a map from this to that itself, which is bijection and respects the structure of the two groups, and that's it. But we will use the first isomorphism theorem. It is much more convenient, and this is what I want to impress upon. So define a map from Z to G. Yeah, so before that, let me also recall a simple fact that we saw as an exercise earlier, I believe. So if G is any group, if G is a group, any group, and little g in capital G, then the map, which sends n to, or let me not write n, k to G to the power k, is a group homomorphism. So this is, we saw as an exercise. So basically I'm trying to say is that it's very easy to throw group homomorphisms from Z. You just pick an element in the target group and that's it. And this is basically the only way to throw group homomorphisms from Z. There is no other way. All right. So let G equals e to the power 2 pi I by n. So this is an element of capital G. This is of course an nth root of unity. And define phi from Z to G as phi k equals G to the power k. So this is a group homomorphism. And now what is the kernel? Kernel phi is those integers such that G to the power k is the identity of the group capital G, but that is actually equal to 1, the number, the complex number 1, which is same as k in Z, e to the power 2 pi I k pi n equals 1. And if you just think about it a little bit, this is equal to nz, which is nothing but nk, k, an integer. So those integers which are divisible by n. So the kernel is precisely nz. So by the first isomorphism theorem, what we have is we have this homomorphism and it factors through Z mod nz because nz is the kernel. This is phi bar. This is the natural projection. This is injective. So this usually injective maps are shown via a hook symbol. We just make a sort of a curvy thing here and that denotes injectivity. So the map phi bar is injective. It is also surjective because every nth root of unity is a power of G. So I'll leave you to check that phi bar is surjective. Although you don't need to really check that because what is the size of this? The size of this is n. And what is the size of that? The size of that is also n. There are exactly n nth roots of unity. This is an injective map. So an injective map from a set of size n to a set of size n has to also be surjective. So you don't really need to check that, but anyway, you can check that by hand. So we have a bijective group homomorphism from Z mod nz to G, and therefore we have a group isomorphism from Z mod nz to G, and therefore these are isomorphic. This may seem like a long-winded approach, but what is the most natural approach to do this? What one would do is pick an element here and find and define a map by picking an element here and sending it to the image here, and then you have to check well-definedness and whatnot. I find this much cleaner, and I would encourage you to absorb this kind of reasoning. Okay. So there is this another sort of a continuous version of the same thing that we discussed. So R is a group under usual addition of real numbers, and Z is a subgroup of R under that. So we can consider this quotient group, and we want to show that this is actually isomorphic to the unit circle. This is unit circle in the complex plane. This is a group under the usual multiplication of complex numbers. So we want to show that these two groups are the same. And again, we will use the first isomorphism theorem. So define phi from R to S1 as phi t equals e to the 2 pi I, what should I write? E to the 2 pi I t, I think will suffice, because t equals 1 maps to identity, and yeah, fine. So that's my map, and easy to check that. Phi is a homomorphism, simply because the exponential thing converts addition to multiplication. Therefore, we have a homomorphism. What is the kernel of phi? Kernel phi is those real numbers such that this equals 1. And this by high school mathematics is basically the set of all integers. Right? So that I leave you to check. So therefore, by the first isomorphism theorem, we have this diagram. So this again is an injective map, simply because we have factored out by the entire kernel. Is it surjective? Well, of course, everything in the unit circle can be written in this way. So it is also surjective. Surjectivity is generally denoted by a double arrow. So this is a surjective map also, and therefore what we have is a bijective group homomorphism from R mod Z to S1, and therefore this is a group isomorphism. That's it. And here it will be even, I think, more pain to directly throw a map from R mod Z to S1 and checking well-definedness and whatnot. Just better to throw a map from R to S1 and then factor it out. So these are some ways to, employ isomorphism theorems. We'll see more applications as we go along. So this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.